Hello, this is Prof. Nanya, so I'll try this again. First recording was dropped by Zoom for some reason, or my internet connection. So we're going to be doing Cauchy-Euler, and I'm going to be deriving why the solutions are the way they are. So let's get started with this. And just get rid of this stuff here. All right, so Cauchy-Euler. Now, I'm going to be focusing on the second order, and what we say applies to higher order as well. So let's assume that we have a is a constant, x squared, y double prime, plus b, x, y prime, plus c, y equals 0. And let's assume interval of validity of 0 to infinity. There's a good reason for that. Basically, you want to be able to divide by this x squared, all the terms. And there's a theory of differential equations that talks about what happens and what kind of singularity this is. We're not going to worry about this right now. We're just going to just make this our interval of existence. And we can use our existence and uniqueness theorems here, where A, B, and C are constants. And the way this is usually attacked is you attempt y equals x to the m and plug in. Now, for right now, m, you can, if you want to think of it as a real number, it's fine, but it's really could be a complex number. So if you take the first derivative, and that does apply for complex numbers as well, and the second derivative, and this is just Calc 1 stuff. And then if you plug this in, if you plug this in this differential equation, you get an ax squared m minus 1, x to the m minus 2, plus b x m x m minus 1, plus c x to the m. Now notice this is why the Cauchy-Euler equations are as they are. If you multiply x squared times x to the m minus 2, we get this right here. And once again, you multiply x times x to the m minus 1, we get a b m x to the m plus c x to the m. But because we're in this interval here, we're not allowing x to be 0, so we can safely divide every term by 0, and we get what's known as the indicial equation. And this is, if you've played around with Frobenius series solutions, it means roughly the same thing. It's used for the same purpose. But most importantly, this is a quadratic. So this is really am squared. And I'm going to do the algebra fast here because I assume that you're reasonably good at algebra. And that's a quadratic in m. And you remember if you had ax squared plus bx plus c is 0, the solutions, well, you know that x is minus b plus or minus b squared minus 4ac over 2a. Well, here the a is the same, the b is b minus a, and the c is going to be the same. So what we have right here is a quadratic, and since this is set equal to 0, only certain things can happen. The first case is two real distinct roots. That's good. So the two real distinct roots case, call them M1, M2, and then two solutions. We could have y1 as x to the m1, y2 is x to the m2, and these form and then if we take the Wronskian of these, Remember, these are distinct. That's the determinant, x to the m1, x to the m2, m1, x to the m1 minus 1, m2, x to the m2 minus 1. We're taking the derivatives in the second row, right? If we take the Wronskian, what we have is m2, x to the m1 plus m2 minus 1. Subtract, same thing, except we have an m1 coefficient. m1 plus m2 minus 1. And this is not 0 because m2 is not m1 on that interval there. So, ta-da! Those are two linearly independent solutions, and life is good. Now, 2, the roots are complex conjugates. That is, let's say m1 is of the form alpha plus beta I, where alpha and beta I are real. Alpha and beta are real. And m2 is alpha minus beta I. Now notice this thing right here. If you dump this in the Wronskian, m1 and m2 are still not equal. So notice if we have m2 minus m1, what we get is we get minus beta I. Okay, minus beta I is minus 2 beta I, and that's still not 0 because beta is not 0, because these are complex conjugate roots. If beta were 0, then we'd have a repeated root, and we're not in that condition yet. Okay, so that's that. Now the issue here is you might say, well, x to the alpha plus beta I, what the heck is that? Well, let's call this u1. And let's call this u2. Now, using Euler's formula, well, this is x to the alpha. Now we have to figure out what x to the beta I is. Let's work on that. Well, when you don't know what to do here, you do the E. Now, I'm going to use log in place of natural log because technically this is a complex number. All right. Oh, I screwed that up a little bit. I'll just, oh, that could be a complex number, x to the beta I. And then as log becomes beta I, natural log of x. Yes, x is a real number, so I sort of pass between this multi-valued log. If you don't know what that means, don't worry about it. It's similar to this. I just can't make myself write ln of a possible complex number. And so now we use Euler's formula. And Euler's formula is e to the beta I is cosine beta plus I sine beta. And we talked about that in class. So this is x to the alpha. Then we have cosine of beta log x plus I sine beta log x. And that's going to be our u1. Now our u2, which is x to the alpha minus beta I, well, that could be x to the alpha, and I'm just going to skip doing this again. You just replace beta by minus beta, and because sine is odd, you get this. Because sine of minus x is equal to sine of minus x is minus sine of x. And cosine of minus x is cosine of x. So we have these two things here. u1 and u2 are linearly independent by the Wronskian. But now, if I take u1 plus u2 and divide by 2 to call that y1, what will happen is when we add these two, these cancel, and we get x to the alpha cosine of beta log x. And then if I take u1 minus u2 over 2I get x to the alpha. Now the cosines cancel, and I get sine of beta log x. And notice the beauty is that these are both real functions. So we have our two linearly independent solutions. So now, what happens if we have the third case? That's where it gets interesting. Where we have one repeated root. That is our initial equation, am squared plus b minus a m plus c is 0, and this is a perfect square. This is a square. That means two things. Using the quadratic formula that we have up here, this one right here. Oh yeah, and I ought to make sure that 2a is there. So the root m, okay, is minus b. So I just did that and reversed this over 2a. So there's your single root. And we also know b minus a squared has to equal 4ac, because what's under the radical has to be 0. So we now have this condition here. So now, and we know that x to the m is one solution. So what do we do? Well, what we do is we go back to our differential equation and we do a reduction of order. And so we attempt the solution y equals u times x to the m, where u is some differentiable function. Now, if we do that, y prime is u prime x to the m plus m u x to the m minus 1. Y double prime is u double prime x to the m plus, now we do the derivative here, m u prime x to the m minus 1. Then we take this derivative, and u prime x to the m minus 1. And then we plus it m minus 1 u x to the m minus 2. Okay. Now what we're going to do is we're going to dump into our original differential equation, right? So we're going to now put this in. And notice these two things combine. So now if we have ax squared y double prime, that's going to be a u double prime x to the m plus 2 plus 2 m u prime times a, okay, a m u prime, right, x to the m plus 1, because we're multiplying m minus 1 times x squared. So we have two of these, we have an m, we have that, plus a m minus 1 u x to the m. Then we go b x y prime is equal to, now I'm going to line these up as perfectly as I can. I'm going to have a b u prime, okay, x to the m plus 1 plus, got to do this, b m u. Then we have x times x to the m minus 1. Okay? And then we now have our c, y is equal to c u x to the m. Now we add these because we're in the differential equation. And when we add these, and this is what's kind of cool here, everything in this box, remember, m is chosen to be a root for this equation here. So what happens is what you can do is you can factor out a u x to the m. What we have in this box is a m minus 1 plus b m plus c, all multiplied by, and I'll just write this over here, u x to the m. Well, all this is 0 because that's m is a root of that quadratic. So those are gone. And when we get the following differential equation, a u double prime x to the m plus 2 plus, now what do we have here? We have a 2am plus b u prime x to the m plus 1, and that's still 0. Now we use the fact that we're in the interval of validity 0 to infinity for x to the m, so we can divide both sides. We can divide through by x to the m plus 1, and we get the following differential equation. That's now just plain old x. And that's u prime. And now we make the substitution. We let v equal u prime. V prime is u double prime. So we now have a v prime plus 2am plus b v. And we can solve that. And the way we can solve that is we can separate the variables, or we can use linear first order. I will separate the variables. So we have a dv dx is equal to minus 2am plus b v. Okay, and there's an x here. That's important. Then division, what we have is we now have dv, and I'm going to do the old sleazy thing here. dv over v is equal to minus 2am plus b divided by a. We divided through by v, so we now got to multiply through by dx, and I know that's not really math, but good enough. We'll just call it a differential form and be good with it. Now we have that. We can now do the old integral. Integrate both sides with respect to x. Left-hand side, natural log of v. This side right here, well, we get minus 2am plus b over a, natural log of x. And we don't really need the absolute values, but I'm going to call this k. Now, what we can do is we use the property of logs. So natural log of v is equal to natural log of x raised to this kind of weird power. It's not going to be that weird after all. Plus k. Then we take e of both sides. And if we take e of both sides, what we get is v is equal to, well, e to this is, we get this as a constant. We get an e to the k. And e to this is just this. Now, before I keep carrying this along here, what I'm going to do is I'm going to let e to the k equal 1, or k, let the whole thing equal 1, or k equal 0. So I'm going to let v equal x to this weird power. Now, remember what m is. It's 2a. M, remember, was a minus b over 2a. plus b, all divided by a. And look what happens. The two a's cancel. We get a minus b plus b. And that's x to the minus a over a, which is x to the minus 1. Ha! So if v is x to the minus 1, and that's u prime, iterate, and that's going to be log of x plus some other c. Now we'll let c is 0 here because we have a choice. So our new thing, this is now our u. So your u is natural log of x. So your new solution is natural log of x times x to the m. Now, we have to show linear independence. So if we take the Wronskian, so we write our things x to the m log x. Now when we differentiate, well, we've got to use the product rule. And then we differentiate log, we get x to the m divided by 1 over x, so we get m minus 1. And let's see if we can squeeze another couple of lines out of here. Maybe, maybe not. I think we can. And so we're almost done. So if you multiply this, we get m x to the 2m minus 1 log of x plus x to the 2m minus 1, subtract m x to the 2m minus 1 times log of x. This cancels, and we get our glorious answer, x to the 2m minus 1, which is not 0. So these are linearly independent. So we have actually derived the three kinds of solutions we have. We have this for the real, distinct. So then we have our real, so yeah, let's go ahead and just do a new one here. So let's summarize this because we just went through the derivation. So basically, summary, again, ax squared y double prime plus bx y prime plus c y is 0. We get the initial equation. So then we have real, distinct, m1 and m2. Then the solutions are x to the m1, x to the m2. Okay, so that summarizes that one. 2, complex conjugate. Alpha plus or minus beta I. Then the two solutions are x to the alpha cosine beta log x and x to the alpha sine of beta log x. And then third thing is repeated root in real. Then you have x to the m is one solution, x to the m, and you slap on a log as the second solution. So these are your two solutions. And that does our, all right. That does it for our thing here. So thanks for watching if you did, and have a good one.